So if we kind of look back at our progress yesterday, this was a big problem. So we had, here's what we started with, right? Rational function. We determined that we had vertical asymptotes at plus and minus 1. We calculated our slant asymptote at y equals x. So everybody close up your screens for just a second. I'll be brief. I'll do my absolute darndest here to be real brief on this. You know how good I am at that. So we took the derivative, which was a little bit of a process, but we came up with a fairly concise answer. Took the second derivative, came up with a simplified answer. And then this was just the process of finding the slant asymptote. I'm going to skip through that for now.
Are you going to find that for the test?
Say that again?
Find a slant asymptote.
Yes, you are. Yeah. And I got a good little trick for you today. I built a little, and I'll put it on my notes too. I built a little example that shows you how to do the thing I showed you yesterday. When it works, it's really slick. So we came up with our slant asymptote. When we divided out x cubed over x squared minus 1, we got the polynomial x plus x over the quantity x squared plus 1, right? In the limit that x goes to infinity, the remainder term goes away. And so we just ended up with the only term remaining then was just x, and so this looks like the line y equals x. And then now we were in the process of building our table. So there was our first derivative, there was our second derivative. Our critical numbers of the first derivative, you guys told me, were at 0 and plus or minus radical 3. The zeros of the second derivative, there was only one of them, and it was at 0. And so that's our table, right? And our goal now is to make our sketch. Okay, I'm just going to leverage a little Desmos for this. How about? So there's Desmos. Now, all I've done here is I've added the asymptotes. And I want you to kind of see here how useful that is. I mean, when you look at these asymptotes, boy, that really dictates what the function's going to do, doesn't it? We've got asymptotes at slant asymptote at y equals x and vertical asymptotes at x equals 1 and x equals negative 1. So we just need to fill in the blanks. Okay, so on our table, oh, Seth reminded me, we don't know, we know what's happening over here. To the left of this first vertical asymptote at x equals negative 1, we had a first derivative critical number at which the second derivative was negative, and so that's a minimum. And the concavity is negative everywhere, right? So we could pretty much fill in that part, couldn't we? Let's do that. So that's going to look like, doesn't that mean it has to look like that? Right? How else could it? We have a maximum at negative radical 3. Well, there's our maximum, right? If I pick that point, negative 1.732, that's square root of 3, right? So there's our maximum. If the concavity is going to be down everywhere, that's really all we needed to know, isn't it? If it's going to be down everywhere, we knew that it had to do that. It's the only way it could possibly be down everywhere and stick to the asymptotes, right? So we knew, I mean, right there we knew we had to have a maximum, and our critical number for the first derivative told us where it was. So that one's taken care of. We could go over and look at the other side. Over here we have at positive radical 3, we have a first derivative equal to 0 where a second derivative is positive, so that means a minimum. What's going to happen over here? Yeah, we're going to get just the mirror image, well, kind of the rotated image of that, right? So that. Right? Everybody agree? Only thing possible, right? Those asymptotes really help. But in the middle, we're not quite sure yet, right? So we got to go figure that out. Test points. What was the suggestion for test points? Okay, so like negative 1/2 and positive 1/2. Which row are we going to work on? Where do we always want to work? Yeah, far down as we can. So let's work on the second derivative. And if I plug in, we just want the sign is all right. So at negative 1/2, I'm going to get negative times positive over negative, right? Everybody agree? So what is that? Positive. So we know we get a positive second derivative there. At positive 1/2, we get positive, positive, negative, right? So negative. So then what's this thing have to do? If it's going to be, yeah, if it's going to be concave, what was it again? It was negative on, no, positive on the left, negative on the right. Yeah, so what's that have to do then? It's going to be positive, it's got to be doing that, right? And then that's going to be negative. So it's going to have to just do one of those little numbers. And if we want to add a point to anchor that, we can do that as well. What's the value of the original function? I don't think I have that on this page. There's the original function. What's the value of the function at 0? 0. Right, so we could add this point. And then here's our function, right? And that would have been a pretty easy one to sketch too. We could have gotten that pretty accurate. Okay?
Because at 0, f prime equals 0, is there the tangent line 0?
It is, right. So the fact that f prime is 0 is a good question. Seth's question is this fact right here. What's that mean? Well, that does mean horizontal tangent line. It's just not an extremum. It's a point of inflection instead. Okay. I had a little bit of a brain fart yesterday when I was talking to you about the symmetry thing. But what I told you the day before is right. If you have an even function over an odd function or vice versa, if the top is all odd and the bottom is all even or vice versa, that does count as odd. So this one is odd over even, right? So odd over even is odd, right? What is odd symmetry? Let's look at that while we have the graph up. What kind of symmetry is odd symmetry? Even symmetry is reflective symmetry over the y-axis, right? And what's odd symmetry? Remember? What about are we folding it over the origin? Rotating, right? If it's point symmetry, that's rotational symmetry. So if I put a tack in this function right there, and I spun it around that tack 180 degrees, wouldn't the green lobe end up down there, and the blue one up there, and it would look exactly the same? So that's odd symmetry, right? So we could have, and in this case it probably didn't help that much, but what if this were a really nasty function that had lots of trig parts involved, then it might have been to our benefit to just do half of this thing, right? Theoretically, being as this is an odd function, we could have just done this. We could have just said, oh, I did that twice. Theoretically, we could have just done this, right? We could have just said, could just block out half of this thing.
Well, I think that was cool.
It's like at the top half, yeah.
Can you bring it forward a layer?
Yeah, I think I can go like this. That works great. It's probably a million. Oh, yeah, that's good deal. Anyway, I could have. Yeah, I could have just blocked out the left half, for example, and done the right half. And then from symmetry, I could have filled in all the blanks on the left half without having to do any calculus, right? Yeah, with even, it's easier, right? With even function, they're going to be identical. With this one, because we have think you guys told me what the test was for odd symmetry. F of x is equal to negative f of x, right? And so f of negative x equals f of negative x equals negative f of x. So I would know that if that's an x and that's a negative x, then the y values would have to be opposites, for example. What would that do to the derivatives? If you look at our picture, where's our picture? That one. Notice that what that tells us is where the derivative is going to be positive. Like let's say we go out to 5. If the derivative is positive here, what's it going to be here? It's going to be the opposite of that, isn't it? Right? What's it going to do to the second derivatives if we rotate something? Well, they're going to go from positive to negative values as well, right? Everything's going to get multiplied by -1, all the function and the derivatives. If I had an even function, like a parabola, for example, they're all going to be equal. Everything's exactly equal, right? It's just a mirror image. Those are easier to do. Okay. Okay. Last thing. Okay, yeah, I want to take you through just one super quick example here of when you can use a trick. So if we wanted to find end behavior, you guys could all tell me this is a slant asymptote, right?
Yes.
And one method for doing this would just be to use long division, right? And that's going to always work. So I could divide this out. If I use long division, I'm going to end up getting, because the top is 1 degree higher than the top, the polynomial, I'm going to get a line plus some remainder term, which will go away if I let the limit approach plus or minus infinity. Let x approach plus or minus infinity. But here's what I was trying to show you yesterday. And actually, you know, I don't know if I'd ever even done, I'm sure I had, but I don't remember if I'd ever even done this before. But it just, if I hadn't, I don't know why. Because this works pretty well. This is a pretty slick way to do it. If the bottom factors, right? If the bottom factors, like in this case, I can factor the bottom into x minus 3 times x plus 2. So I could then, I've got a factor divided by a product of factors. Well, everybody would agree that's the cubic on the top divided by the product is exactly the same thing as pulling the 1 over x minus 3 out in front, right? No big deal. Okay. So now notice that I'm enclosing all this in limit notation. This is only going to work if we're trying to find end behavior. Otherwise, we couldn't do this. But if we're taking a limit as x approaches plus or minus infinity, then what is, you know, this guy right here is really easy to do synthetically, right? I've got a linear factor on the bottom, and so my coefficients are 1, 0, 1, -5. Put the 0 at the bottom out front, and I can pretty easily get this result, right? So that corresponds to x squared minus 2x plus 5 plus -15 divided by x plus 2, right? Okay, so we make that conversion. Out in front, I've still got this 1 over x minus 3. If I distribute that through, right, if I distribute the 1 over x minus 3 through, I'm going to get the yellow polynomial part divided by x minus 3 plus this red part over here times 1 over x minus 3. So I'd end up with -15 over x minus 3 times x plus 2, right? But in the limit that x goes to plus or minus infinity, you guys see that that's going to go to 0, right? Because I'm going to get big powers of x on the bottom that are going to explode, right? So that part just goes away, which leaves us only with this other part, right? That part is also easy to do synthetically, right? We can go through and the coefficients become 1, -2, and 5, and the 0 of x minus 3 is 3, and I can pretty easily do that and get this result. Well, what does that result mean? X plus 1, there's the line part, plus 8 divided by x minus 3, right? But once again, in the limit that x goes to plus or minus infinity, that second part is going to vanish, right? And so all I'm left with is the limit of x plus 1, which just means that that's the slant asymptote, right? All the other terms went away, okay? That's a lot of work, but that can all be summarized really simply like this. 2 steps of synthetic division, right? The first step was the yellow step that we did, right? When we divided this first polynomial, the top polynomial by either one of those. We just chose x minus 3, right? And we got this result. The last term went away. The second step of synthetic division was further along when we did the quadratic divided by x minus 3, and we got this result. So all we have to do, we can combine both of those synthetic division steps like that. So this is really easy. If the bottom factors, look what this is doing. So we know the bottom factors into x minus 3 times x plus 2. So the 2 zeros of the bottom are 3 and negative 2, right? It doesn't matter which one you use first, but those are going to be the numbers out in front of the brackets, right? And you see what I'm going with this? This is really cool. The original coefficients of the numerator of this whole thing are 1, 0, 1, and negative 5. So look how easy this is now. We're just going to set those up. We'll do the first synthetic division iteration first. So bring the 1 down. 1 times 2 is 2, plus 0 is 2. Did I make a mistake? Oh, negative 2. Negative 2 times negative 2 is 4. 1 plus 4 is 5. What goes there?
Okay.
Who cares? Because it doesn't matter, because whatever's there, it's going to go away anyway, right? In the limit that x goes to infinity or negative infinity, that's going to 0 anyway, so just ignore it, right? You don't even need that part. Isn't this cool? Then you go down here and do it again. You bring the 1 down. 3 times 1 is 3, plus negative 2 is 1. And then once again, who cares? That's our answer, right? How quick is that? X plus 1 is the slant asymptote, right? So that only works if you've got a factorable denominator, but when you do, that's so much quicker than doing a big long division problem, right? Okay. I'll put that in the notes just so you have access to it. But okay, you can work.
I have a quick question.
Yep.
If you have one of those funky side